Welcome! In this session, we'll be exploring an exciting problem from LeetCode, number 1424, Diagonal Traverse 2. This problem falls under the category of array manipulation and involves traversing a 2D array in a diagonal pattern. We'll discuss the intuition behind the solution, analyze its complexity, and cover the key takeaways. Let's dive in. In this problem, we are tasked with traversing a 2D array of integers in a specific diagonal order. The traversal begins from either the first row or the last column and progresses diagonally in a bottom-left direction. For each diagonal, we process elements starting from the topmost one and work our way down to the bottommost element. The result of this traversal is a single, flat list containing all the integers in the order specified. The given input format is a list of lists, where each inner list may have a different length. Our goal is to return a single list as the output, representing the diagonal traversal of the input. This approach allows us to handle irregularly shaped 2D arrays, making the problem both unique and versatile. To better understand the problem, let's consider an example where the input is a 2D array nums with 3 rows, 1, 2, 3, 4, 5, 6, 7, 8, 9. The output for this example would be 1, 4, 2, 7, 5, 3, 8, 6, 9. Here's how we achieve that. The first diagonal starts at nums 0, 0, which is 1. The second diagonal starts at nums 0, 1, and includes elements 4 and 2. The third diagonal starts at nums 0, 2, and includes 7, 5, and 3. The fourth diagonal begins at nums 1, 2, and consists of 8 and 6. Finally, the fifth diagonal starts at nums 2, 2, and contains only 9. When we combine the elements from all these diagonals, we get the final result. This demonstrates how the traversal proceeds diagonally and collects elements systematically. Now, let's look at another example to solidify our understanding. Suppose the input nums is 1, 2, 3, 4, 5, 6. The output for this input is 1, 3, 2, 4, 5, 6. Here's the step-by-step breakdown. The first diagonal starts with nums 0, 0, which is 1. The second diagonal starts at nums 0, 1, and includes elements 3 and 2. The third diagonal begins at nums 1, 0, and contains 4 and 5. Finally, the fourth diagonal starts at nums 2, 1, and consists of just 6. Combining these diagonals gives the output list 1, 3, 2, 4, 5, 6. Notice how this example highlights the flexibility of the traversal, as it adapts to rows with varying lengths seamlessly. For a slightly more complex case, consider the input nums as 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. The output for this input is 10, 11, 13, 12, 16, 14, 17, 15, 18, 19. Let's break it down. The first diagonal starts with nums 0, 0, which is 10. The second diagonal begins at nums 1, 0, and includes 11 and 13. The third diagonal starts with nums 1, 1, and contains 12 and 16. The fourth diagonal includes 14 and 17, followed by the fifth diagonal, which consists of 15 and 18. Finally, the sixth diagonal starts with nums 3, 3, which is 19. By combining all these diagonals, we arrive at the final result. This example demonstrates how the traversal handles deeper and more irregular 2D arrays while maintaining the diagonal order. To ensure clarity, let's consider some specific edge cases. If the input nums consists of a single row, the output will simply be the elements of that row, as no diagonal movement is required. Similarly, if nums is a single column, the output will be the elements of that column in their natural top-to-bottom order. If any sublists in nums are empty, we can ignore them during traversal, as they contribute no elements. Finally, for large inputs, where nums contains many rows or columns but the total number of elements does not exceed 10 to the power of 5, we must ensure that our solution is efficient and can handle these cases without performance issues. These considerations are critical for building a robust solution that works well across all scenarios. To solve this problem, we first considered a brute force approach. The main idea here is to traverse the entire 2D array and group elements that belong to the same diagonal, identified by the sum of their row and column indices, which we'll call the diagonal index. To implement this, we can use a dictionary where the keys represent these diagonal indices, and the values are lists containing the elements of each diagonal. As we traverse the array, we append each element to its respective diagonal group. Once all elements are grouped, the diagonals are sorted based on their keys, and the values are concatenated to form the final result. However, this approach has some drawbacks. The time complexity includes the cost of sorting the diagonals, and the space complexity can be significant for large or sparse arrays due to the overhead of storing the hash map. This makes the brute force approach inefficient and less suitable for scenarios involving large datasets. To address the inefficiencies of the brute force approach, we shift to an optimized iterative method. Instead of sorting diagonals after traversal, we process them directly in the required order. Here's how it works: we still group elements by diagonal index using a dictionary or a list of lists, but this time, we traverse the rows of the array in reverse order. This ensures that when we append elements to the diagonals, they are already arranged in the correct sequence. After grouping all elements, we then flatten these diagonals into a single list to produce the final result. This approach eliminates the need for sorting, which improves efficiency. The time complexity is reduced to just the cost of traversing the array, as we process each element exactly once. While we still require space to store the diagonals, this is unavoidable given the problem's constraints. Overall, this method is both faster and more direct, making it a clear improvement over brute force. The optimized iterative approach is the strategy we've chosen for this problem. There are several key insights that make it effective. First, the diagonal index, defined as the sum of the row and column indices, uniquely identifies which diagonal an element belongs to. Second, by traversing the rows in reverse order, we ensure that the elements are processed in the correct sequence as we group them. Finally, flattening the diagonals at the end avoids unnecessary intermediate computations, keeping the implementation streamlined. This method minimizes time and space complexity by eliminating the sorting step and directly addressing the problem requirements. While it does require additional space to store the diagonals, this is an unavoidable trade-off given the nature of the problem. Additionally, the implementation requires careful handling of indices, but this is manageable with attention to detail. By balancing efficiency and clarity, the optimized approach provides a robust solution to the problem. While the brute force method is easier to understand, it is not practical for large or sparse inputs, making the optimized approach the superior choice for both performance and scalability. To solve this problem, we need to traverse a 2D grid and group its elements based on their diagonals. A diagonal in this context is defined by the sum of the row index I and the column index j. For instance, in the example grid shown here, the element at position 0, 1, which is 2, belongs to diagonal 1 because 0 plus 1 equals 1. Similarly, the element at 2, 0, which is 7, belongs to diagonal 2 because 2 plus 0 equals 2. This sum, I plus j, acts as a unique identifier for each diagonal, enabling us to group elements accordingly. Understanding this relationship is the first step in approaching the problem. With this diagonal identification, we can proceed to structure a solution that leverages this property to group and output the diagonals in the desired order. Once we understand how diagonal indices work, we can use a dictionary to group elements by their respective diagonals. The keys in this dictionary are the diagonal indices, I plus j, and the values are lists of elements belonging to those diagonals. To build this dictionary, we traverse the grid row by row. For each element at position I, j, we calculate its diagonal index as I plus j. If this index is already a key in the dictionary, we simply append the element to the corresponding list. Otherwise, we create a new entry in the dictionary with this index as the key and initialize it with the current element. Once we've completed the traversal, we can generate the output by iterating through the dictionary keys in sorted order. For each diagonal, we append its elements, preserving their original order, to the final result list. This approach ensures that we process diagonals from top left to bottom right of the grid, maintaining the required output order. Sorting the dictionary keys is crucial because it ensures that diagonals are processed in the correct sequence, from the top left corner of the grid to the bottom right. For data structures, we rely on a dictionary or hash map to group elements efficiently. This allows for constant time insertion and lookup operations for each diagonal. Additionally, we use lists to store the elements of each diagonal as we traverse the grid, which helps preserve the order of elements within each diagonal. In terms of complexity, the time complexity of this approach is O(m*n), where m is the number of rows and n is the number of columns. This accounts for visiting each element in the grid once and performing dictionary operations. The space complexity is also O(m*n), since we store all elements in the dictionary. With these insights, we can confidently implement the algorithm to group elements by their diagonals. The implementation begins by defining a function group _by_ diagonals that takes the grid as input. Within this function, we initialize an empty dictionary called diagonals. As we traverse the grid, we calculate the diagonal index for each element and add it to the appropriate diagonal in the dictionary. After the traversal, we prepare the result list by iterating through the dictionary keys in sorted order. For each key, we extend the result list with the corresponding diagonals elements, maintaining their original sequence. Finally, the result list is returned. For example, given the input grid 1, 2, 3, 4, 5, 6, 7, 8, 9, this implementation outputs 1, 2, 4, 3, 5, 7, 6, 8, 9. This demonstrates how the elements are grouped and outputted by their diagonals, following the top left to bottom right traversal order. This Python implementation solves LeetCode problem number 1424, diagonal traverse 2, by grouping matrix elements into diagonals based on their row and column indices and then traversing the group diagonals in the required order. The solution starts by importing the default dict class from the collections module. This is used to create a dictionary where the default value for each key is a list. This helps store matrix elements grouped by their diagonal keys without needing to initialize each key manually. We define the function findDiagonalOrder inside the solution class. The input, nums, represents the 2D list of integers. First, we iterate through each row of the matrix using enumerate to get both the row index I and the row values. Within each row, we iterate through each element using another enumerate call to get the column index j and the value val. For each element, we calculate its diagonal key as the sum I plus j, which uniquely identifies the diagonal it belongs to. The value is then appended to the list corresponding to that key in the diagonals dictionary. After grouping all elements by diagonals, we initialize an empty list result to store the final output. The diagonals are processed in the order of their keys, which are sorted numerically. For each diagonal, we reverse the list of elements, as required by the problem, and extend the result list with this reversed list. Finally, the function returns the result list, which contains the matrix elements traversed in the required diagonal order. This implementation is efficient and handles edge cases like empty rows or uneven row lengths correctly. Here, we start by importing the necessary packages and defining our solution class. The method findDiagonalOrder takes a list of lists of integers as input and returns a single list of integers representing the diagonal traversal. First, we use a hash map to group the elements by their diagonal keys, which are calculated as the sum of their row and column indices, i.e., I plus j. This allows us to efficiently group elements that belong to the same diagonal. Inside the nested loops, we iterate through each element in the input list, calculate its diagonal key, and add it to the appropriate group in the hash map. If the key does not yet exist in the map, we initialize it with a new array list. We also keep track of the highest key value encountered, which will help us later during traversal. This first step ensures that all elements are categorized by their diagonal levels. Once we have grouped the elements by their diagonal keys, we proceed to collect the diagonals in the desired order. To do this, we iterate through all the keys from 0 to the maximum key value. For each key, we retrieve the corresponding list of elements from the hash map. Since the problem requires us to traverse diagonals in reverse order, we iterate through the list from the last element to the first and add these elements to the result list. Finally, after processing all diagonals, we return the result list, which now contains the elements in the correct diagonal traversal order. To solve this problem, we start by initializing a default dict called diagonals, which will group elements based on their diagonal keys, calculated as the sum of their row and column indices, I plus j. Additionally, we create an empty list called result to hold the final output. Next, we process the input matrix row by row. For the first row, 1, 2, 3, the elements are added to their respective diagonals. The value 1 is added to diagonal 0, 2 to diagonal 1, and 3 to diagonal 2. Moving to the second row, 4, 5, 6, 4 is appended to diagonal 1, 5 to diagonal 2, and 6 to diagonal 3. Finally, for the third row, 7, 8, 7 gets added to diagonal 2 and 8 to diagonal 3. At this stage, all matrix elements are grouped by their diagonal keys in the diagonals dictionary. With the diagonal groups formed, we now construct the final result. The diagonals are processed in the order of their keys. For key 0, the diagonal 1 is reversed and appended to the result, giving 1. For key 1, the diagonal 2, 4 is reversed to 4, 2, and added, updating the result to 1, 4, 2. Similarly, diagonal 3, 5, 7, for key 2 is reversed and appended, resulting in 1, 4, 2, 7, 5, 3. Lastly, diagonal 6, 8, for key 3 is reversed to 8, 6, and appended, producing the final output 1, 4, 2, 7, 5, 3, 8, 6. This sequence demonstrates how we maintain the diagonal order and reverse each group before adding it to the result. In a second example, the input matrix is 1, 2, 3, 4, 5, 6. We begin with a defaultic diagonals and an empty list result. For the first row, 1, the value 1 is added to diagonal 0. Next, for the second row, 2, 3, 2 is added to diagonal 1 and 3 to diagonal 2. For the third row, 4, 5, 6, 4 is appended to diagonal 2, 5 to diagonal 3, and 6 to diagonal 4. After traversing all rows, the diagonals dictionary now groups the elements by their diagonal keys, ready for the next step of constructing the output. To construct the result, we process the diagonals in the order of their keys. Starting with key 0, the diagonal 1 is reversed and added to the result, producing 1. For key 1, the diagonal 2 is reversed and appended, resulting in 1, 2. The diagonal 3, 4, for key 2 is reversed to 4, 3, and added, giving 1, 2, 4, 3. For key 3, the diagonal 5 is reversed and appended, resulting in 1, 2, 4, 3, 5. Finally, for key 4, the diagonal 6 is reversed and added, leading to the output 1, 2, 4, 3, 5, 6. This ensures the values are listed in the correct diagonal order. In the third example, the input matrix is 10, 20, 30, 40, 50, 60. Once again, we initialize a defaultic diagonals and an empty list result. For the first row, 10, 20, 10 is added to diagonal 0 and 20 to diagonal 1. For the second row, 30, 30 is appended to diagonal 1. For the third row, 40, 50, 60, 40 is added to diagonal 2, 50 to diagonal 3, and 60 to diagonal 4. By the end of this step, all elements are grouped into their respective diagonals in the diagonals dictionary. To finalize the result, we process diagonals in ascending order of their keys. For key 0, the diagonal 10 is reversed and appended to the result, giving 10. For key 1, the diagonal 20, 30 is reversed to 30, 20, and added, resulting in 10, 30, 20. The diagonal 40 for key 2 is reversed and appended, updating the result to 10, 30, 20, 40. For key 3, the diagonal 50 is reversed and appended, yielding 10, 30, 20, 40, 50. Finally, for key 4, the diagonal 60 is reversed and added, producing the final output 10, 30, 20, 40, 50, 60. This process ensures the diagonal order is preserved, and each group is reversed before appending to the result. To analyze the time complexity, we start by breaking the function into two distinct steps. In the first step, we group elements by their diagonal key, which is determined by the sum of their row and column indices, I plus j. Here, the outer loop iterates through the rows of the input nums, and the inner loop goes through the elements within each row. If we let m represent the number of rows and n represent the total number of elements across all rows, then each element is processed exactly once and added to the appropriate diagonal in our default dict. This makes the total work in this step proportional to O, n. In the second step, we handle the diagonal keys. First, we sort these keys, which represent the indices of the diagonals. The number of unique diagonal keys is at most m plus len, nums, -1, 1, which corresponds to the total number of distinct diagonals. Sorting these keys has a cost of O, m asterisk log, m. After sorting, we reverse the elements of each diagonal and append them to the result list. Since the total number of elements processed remains n, the reversing and appending have a combined cost of O, n. These two steps together form the basis for the function's overall time complexity. Now, when we combine the costs from both steps, the dominant factor in our time complexity comes from sorting the diagonal keys, which is O, m asterisk log m. Adding the O, n, cost of processing all elements, the total time complexity is therefore O, n plus m asterisk log m asterisk asterisk. Shifting to space complexity, the function uses additional space in three primary ways. First, the default dict stores lists of elements for each diagonal, and the total space required for this storage is proportional to the total number of elements in nums, which is O, n. Second, we need temporary space to store and sort the diagonal keys. Since the number of unique diagonal keys is O, m, sorting them requires O, m, space. Lastly, we have the result list, which stores all elements in their final order, requiring an additional O, n, space. These components together determine the total space complexity. The overall space complexity of the function is determined by the sum of the space for storing diagonals, the result list, and the temporary space for sorting. With O, n, for the diagonals and result combined, and O, m, for sorting keys, the total space complexity becomes O, n plus m. Comparing this to a brute force approach helps highlight the efficiency of the optimized solution. In a naive method, we would manually traverse each diagonal using nested loops. For a rectangular grid, this would result in a time complexity of O, n asterisk m, and for jagged arrays, the complexity could be even worse. However, the space complexity for the result would still remain O, n. In contrast, the optimized approach leverages hashing to group elements efficiently by diagonals, reducing the traversal time to O, n, and leaving only the sorting overhead of O, m asterisk log, m. This makes the optimized solution significantly faster and better suited for handling jagged arrays. Finally, let's consider the best, average, and worst-case scenarios for this solution. In the best case, the number of diagonals is minimal, such as when all elements are in a single row or within the same diagonal. Here, the time complexity is dominated by O, n, as sorting the diagonal keys becomes trivial. In the worst case, the input contains many rows and columns with sparse elements, resulting in the maximum possible number of diagonals. Under these conditions, the time complexity reaches O, n plus m asterisk log, m. For the average case, the runtime typically remains close to the worst case, as sorting diagonal keys is an essential step. Regardless of the input structure, this solution is highly optimized for organizing jagged arrays in diagonal order, ensuring efficient handling of a wide variety of scenarios. One of the most common mistakes when solving diagonal traversal problems is grouping elements incorrectly by diagonal. It's crucial to remember that all elements on the same diagonal share the property ij, where I is the row index and j is the column index. Misidentifying this relationship will result in incorrect groupings and, ultimately, an incorrect result. Another frequent error is not paying attention to the required ordering of diagonals during concatenation. For example, if a problem specifies that diagonals should be processed from top to bottom or bottom to top, failing to follow this order can lead to output that doesn't match the expected format. Lastly, overlooking edge cases like single-row or single-column matrices can be problematic. These cases often have simpler behavior but require explicit handling to prevent runtime errors or out-of-bounds issues during traversal. Another pitfall to be aware of is relying on inefficient brute force traversal. Iterating over the entire matrix repeatedly may seem like a straightforward approach, but for larger matrices, it quickly becomes computationally expensive, often leading to time complexities of O, n squared, or worse. This is far from optimal and can result in performance issues. Additionally, incorrect memory management is a concern, especially in languages like C++ or Java. When using temporary storage structures like hash maps or lists, improper allocation or cleanup can lead to memory leaks or excessive memory usage. These issues not only hurt the efficiency of your solution but may also cause unexpected crashes. It's important to manage memory responsibly to ensure your program runs smoothly. To excel in interviews, it's essential to recognize patterns involving diagonals in 2D arrays. The relationship IJ is often the key to grouping elements correctly or identifying diagonal indices. Efficient solutions should aim to process each element only once, achieving an optimal time complexity of O(n*(m) for an nxm matrix. It's also a good idea to ask clarifying questions during interviews, such as confirming the required diagonal ordering or understanding constraints on the input size. Testing your solution against edge cases is another critical step. Examples include empty matrices, 1x1 matrices, and matrices with only one row or column. Lastly, hash maps, or dictionaries, are frequently used to store diagonal groups efficiently. Be prepared to discuss their trade-offs compared to other data structures, such as arrays or linked lists. Several related problems can help strengthen your skills with diagonal traversal and matrix manipulation. For instance, problem 498, diagonal traverse, involves navigating matrix diagonals and returning elements in a specific zigzag order. Problem 1424, diagonal traverse 2, is similar but deals with jagged arrays where rows have varying lengths. Problem 54, spiral matrix, focuses on traversing a matrix in spiral order, which can sometimes be combined with diagonal traversal in interview variations. Lastly, problem 73, set matrix zeros, while not directly related to diagonals, emphasizes the importance of efficient matrix traversal. When exploring alternative approaches, hash map grouping is a common method, where you use IJ as the key and store diagonal elements as values. This is efficient for grouping but requires extra space for the hash map. Another option is in-place modification, where you temporarily store diagonal groupings within the matrix itself. While space efficient, this approach can be harder to implement and debug. Stacks or queues can also be valuable tools for diagonal traversal, depending on the required order of processing. For instance, if the problem specifies reverse order, a stack is an excellent choice since it naturally supports last-in first-out behavior. For direct order, queues are more appropriate as they follow a first-in first-out structure. These data structures are useful for maintaining the intended order, but they can add implementation complexity. It's important to weigh the benefits of these approaches against their potential drawbacks, ensuring that your solution remains both efficient and easy to understand. Great job! We've covered the problem diagonal traverse 2, explored its brute force solution, and discussed its key concepts. This is a valuable problem to practice diagonal traversal in 2D arrays. Thank you for joining, and don't forget to like, subscribe, and share. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!